Hello, everybody. Welcome back. Today we're going to be looking at Unit 3.8, which is called the Representations of Solutions, which basically means being able to look at solutions in a more visual way to understand what's going on. So let's get started. The first thing that we need to understand when a solution is formed, when something dissolves in something else, are the different steps that take place in that process. And it primarily occurs in 3 steps. The first step is expanding the solute. Okay, and I say in parentheses, that's an endothermic process, and we'll talk about that later on. But what I mean here is we're going to, the solute is pulled apart. Now, depending on what the solute is, whether it's ionic or a covalent solute, could mean different things. Expanding or pulling apart an ionic solute means breaking what? Breaking ionic bonds. If you're pulling apart a covalent solute, what are you breaking? You're breaking intermolecular forces. But no matter the situation, those are both scenarios that require energy, and that's why it's endothermic. But again, we'll talk about that part later on, the energy aspect. Step 2 is expanding the solvent particles. The solvent particles have to physically move away from each other to make room for those solute particles to get in there. Again, it's also going to be an endothermic process, something that requires energy because we're breaking things. And typically we're going to be talking about very often water as our solvent. And what is it that would be required to pull 2 water molecules apart? Breaking those intermolecular forces again. The third part, which is really the most important step, is how do the solute and solvent interact with one another. Some solutions, the solute and solvent, are going to have very strong forces of attraction between them, and that would be a solute that very readily dissolves in that solvent. Sometimes the attraction is very, very, very weak, and that's usually a situation where there isn't going to be solution formation. Now, there's a phrase that you likely learned in Chem 1, like dissolves like. And it's a good phrase, but we're going to talk about when not to use it. Okay, but in general, let's talk about why it is a good phrase. Like dissolves like typically means polar solutes will dissolve in polar solvents, and nonpolar solutes will dissolve very well in nonpolar solvents. Okay. So that's what that phrase means. We'll talk about in just a minute when do you not want to use that phrase. So what this unit really hammers home is, can you visualize what is going on when a solution is formed? Okay, so in this picture that we've got here, our solute is a crystal of sodium chloride, and we're going to dissolve it in water. So let's review those 3 steps of solution formation. Step 1, we pull the solute apart. And in this case, pulling the solute apart involves breaking ionic bonds. Step 2, expand the solvent. The water molecules are going to pull apart from each other to make room. That's breaking intermolecular forces. And step 3, how do the solute ions here interact with the solvent particles? And that's the most important step. And I want you to notice on the top part of this picture, The sodium ion is being surrounded like a cage almost with these water molecules. And this is really what happens. The water molecules aid in the process of ripping the solute apart, and they surround each ion. Please notice in this top part of the picture, the sodium ion, which is positive, is being surrounded not just by the waters, but the oxygen sides of the water. And I want you to think about why that might be. Remember that water is a polar molecule, and oxygen is a pretty electronegative element. So the oxygen side of water is going to carry a partial negative charge, which is why it's going to be attracted to the cation sodium. Okay, and then look at the picture on the bottom. The negative chloride anion is also being surrounded by waters, but to be more specific, the positive hydrogen sides are facing that anion. And it's really important that you understand that what this drawing is represented, because sometimes you will have questions on the AP exam in free response where they ask you to draw something just like this. They're going to want to see the charges on the ions, okay, the solute particles. They're going to want to see multiple water atoms, or water molecules, excuse me. They're going to insist that you have the water molecules drawn appropriately, meaning for the sodium that the oxygen sides of the water are facing that cation and the hydrogen sides are facing the chloride anion. And the last part to this, and I put on the slide, size does matter. They will want to see that you've drawn the chloride anion larger in size than the sodium ion cation. Okay. In general, ladies and gentlemen, anions typically are larger than cations, and the AP graders will want to see that. They want to see that you understand that. So size does matter here, right? Now, what about something, we've been talking about when a solution forms, but what about when it doesn't? Okay, like oil and water. Okay. And a lot of times students will say things like, well, because like dissolves like, and these things aren't like. All right. You can't say that. In fact, to be honest, that term, that phrase, like dissolves like, is helpful for understanding, but people, please, please, please don't ever write that on a test or an AP exam. The graders will not accept it. Okay, so why do like things dissolve like things? Because the solute and solvent attract to one another. So why don't oil and water mix? Okay, because the attraction between oil and oil, okay, and in case you don't know, oil is a very non-polar substance. Water, of course, is polar. Okay. The reason they don't mix is because the attraction between the oil molecules and the attractions between the water and water molecules, the attractions to themselves are stronger than the attraction to something else. That's why oil and water don't mix. Okay. Please don't use the phrase like dissolves like as an explanation, because that's not going to be accepted. All right. So the oil to oil attraction between two oil molecules is stronger than between oil and water. Okay. They attract to themselves more than they do to something else. When is a solution actually formed? Because the solute and solvent attract to each other more than they do to themselves. That's when a solution is formed. Okay, please don't use like dissolves like. Okay, now, as I said, guys, many times in free response, you will be asked to draw particle diagrams like this, okay? And there's one thing on this diagram that I don't like, and I'm going to point it out in just a second. But not only do you need to draw appropriate charges on your ions and things like that, but the number of particles that you draw is also important. Okay, for example, if you will count with me, how many copper ions are drawn in this picture? 1, 2, 3, 4. Okay, well, if there's 4 copper ions, look at the ratio here. Copper to nitrate, they're in a 1:2 ratio. You'll notice in the picture there are 8 nitrate ions, and there should be. However many copper ions there are, there should be double that number of nitrates. So if you were asked to draw a solution of copper nitrate dissolved in water, for example, and I realize this picture does not have the waters drawn in, I'll show you what that would look like in just a second. It would be important for you to draw the appropriate number of particles. If you're going to draw 2 copper particles, then you need to draw 4 nitrate particles. Okay. If we were asked to draw the waters, I might draw something like this, where you can see that I've got the 2 hydrogens facing that negative nitrate. Remember, the positive side of the water is the hydrogen side. Facing the copper ions, I'm going to have the oxygen side. They're like little Mickey Mouses. Okay, that might be an acceptable way to draw waters in there. Okay, that shows the graders that not only do you know that water is going to surround these particles, but you've got the water particles facing the correct direction. Okay, they're oriented correctly. The only thing I don't like about this drawing in front of us is, remember what I said, size does matter. Those nitrate ions should be drawn a little bit bigger than the copper ions. Remember what I said, anions in general are larger than cations. So that's my only complaint with that drawing there. So I've hoped you've learned a little something today. I think these particulate diagrams and drawing them out is really important because it shows that you truly do understand on a particle level what is going on. So this is a really important thing. It's covered on the AP exam a lot. So as I said, I hope you've learned a little something, and I look forward to seeing you next time.